in LP metrics. This is joint work with an undergrad at University of Michigan and a PhD student at Rutgers. So in order to sort of convey what the results in this work is, I want to sort of first describe a program that I'm working on. It's hardness approximating geometric problems in general. And I want to, by telling the program, it will become clear what the results mean. So if you look at from a complexity point of view, and you put things on a scale telling which problems have more structure and which have less. Typically, it's easy to prove hardness when there is less structure in a problem, because then you have more freedom to do reductions. So you would possibly have here circuit SAT, which is the easiest to prove hardness approximation results for. And then you have what is called the PCP theorem, from which you get what is called label cover. And then you start having these set systems like set cover, set packing, max coverage, and things like that, which are set systems problems. And then you started, if you look at the history, then we started proving things which are local, like 3-len, 3-sat. And then there were all these graph problems for which we started proving things, like clique, vertex cover, max cut. And then there are these geometric problems for which algorithm people care about a lot, but there are very few hardness results, like PSP, clustering, Steiner Tree. So the program I'm referring to is to prove sort of like the tight hardness approximation results for these three problems. And there's this general intuition that I have that all of these should come from very structured instances of set cover or set systems in general. So we already have some essentially more or less the tight bounds under plausible conjectures for clustering, which is called JCH. So assuming JCH, you can get the tight results for clustering. And this paper starts to do the same thing, but for Steiner tree.
Good problem with three-dimensional matching in this context, which is also used in.
I would just put it as set mapping. It's just set packing with bounded sets. So that's what I call by structured set systems. And there is another thing, which is how do we prove these things? Typically, if you look at whatever the known results for these things are, they take tight hardness approximation results for like say 3-len or 3-sat, and then do gadget reductions. And if you don't start off with the right problem, regardless of how sophisticated the gadget is, you won't get the right answer. So the framework which I'm working now in is, I believe that fundamentally all these problems should have complex starting points, which are combinatorial. But once you assume or prove the hardness for these combinatorial problems, straightforward embeddings. So the embedding should be straightforward. Once you prove the hardness for this, it's a different framework in which to prove things. So the whole emphasis or the heavy work is done by the combinatorial thing. This also comes from intuition that these problems, the geometry doesn't really add too much. It's really the combinatorial things that are underlying that make it hard. Okay, so much background. Let's define the Steiner tree problem. So in the Steiner tree problem, you're given a metric space, let's say. So delta is some distance function, x is some set. Think of x as Rd and delta as your empty metric space, if you want. And the input is a point set P and say some integer, some opt that you want to check alpha. And the goal is to find what is called a Steiner tree. So your output would be the spanning tree on P union S. So P is your input, and S is any point set we can pick from X. So S is something we can pick such that the cost of this spanning tree, which is just the sum, you look at every edge can be associated with the distance between the pair of points, and then you sum over all the edges. So the such that the cost is at most alpha. Okay. Like for instance, let's look at this example. We have 3 points in the Euclidean plane, and they are all at distance one from one another. And I set alpha to be square root 3. Now, naively, if you take any MST of these 3 points, it's going to be at 2. But if you include this Steiner point, which is the middle, the centroid of the things, then this distances are all 1 over square root 3. And if you sum them up, it's square root 3. So you do have a minimum spanning tree by including this point, this cost distance. So this would be the spanning tree, these 3 things. So in this talk, I'm going to be interested in what is called the discrete Steiner tree, where as part of the input, we are also given a set of facilities. And you can only pick your Steiner points, which are the additional points you pick from the set of facilities. So this is called the discrete Steiner tree problem. So what do we know about this? So in the discrete Steiner tree problem, this was one of the classic NP-hard problems that was studied. And in the general metrics, where all you have is that the points, the distance function behaves as a metric space, that's it. In general metrics, Karthik showed that this is NP-hard. So suppose you're given a metric space, let's say through a graph. So you're given a graph in which this is your set P, and this is the remaining points of space. And then the distance is just the graph distance that you have. Then computing the spanning tree, connecting all the points in P, it's NP-hard to find the optimal spanning tree for this. So this is one of the classic NP-hard problems. Okay. At the same time, when things are NP-hard, what we, yeah? Oh, it's just a polygon. Anything like in cube and into the cube. One more technical thing is P is called the set of terminals. I'll be using this terminology. P is called terminals, F is called facilities, and the points that we actually use is called Steiner points. So in general metrics, when the metric space is given to you hard-coded as part of the input, and you're given a subset of the metric space as your terminals, finding the min-cost spanning tree in which can include Steiner points in the solution, this is NP hard. And then you want to ask, the classic way to cope with NP hardness is to find approximation algorithms. And there's a very simple two approximation. Which is just take a metric completion and find the spanning tree on P without using any Steiner points, and that gives you a two approximation. And after a series of works which are more impressive than the next, I think the state of the art is ran 4 plus epsilon, which is 1.39. So you can do 1.39 approximation in polynomial time. This was yeah, this was the Bierka, Grandoni, there are a few more authors there.
So one question, like in this, let's say number of terminals are constant, 10 or 15, but F can be large. In that case, it is still NP hard or?
No, but then your input is still, F is given to you as part of the input, right? So your input, you have enough time. So I'm guessing there are these FPT algorithms that start to come in. Because they're K, the parameter, and I'm not sure either if it's the W1 hard or an FPT, and depending on that, you'll get the answer. Right, so from the approximation point of view, they reach till 1.39, improving on 2. From the hardness of approximation point of view, need to know the names. So this one, how do you pronounce this? Let's see. Chlebík and Chlebíková. Chlebík and Chlebíková showed that to approximate it to a factor 96/95, which is like 1.01, this is still NP hard. So you cannot approximate it to a factor. So you don't have PTAS, for instance. But then there's still a huge gap between these two things, right? So
I have one question in the non-discrete. I mean, when the first case which you showed.
Yeah.
In that case, is what's known in that case?
Right. So in the non-discrete case, let's start with first saying that you cannot look. So x and delta you cannot give it as part of the input, right? Because then it falls to a discrete case. So you're asking possibly in Euclidean space and things like that. So in the Euclidean space, we know it's NP hard. When it's fixed dimensions, there's a PTAS. So when the dimension is 2 or 5 or whatever, it is open to rule out a PTAS in, say, log n dimensions or not. We believe it's supposed to be APX hard, but it's still open. It's one of the most I don't know. I'm very interested in that question. I've been thinking about it for a while now. The problem comes because there are these things called Steiner ratio, which are studied in the mathematical context, and we don't have a good answer there. So if you don't even know what Steiner trees are good, how will you prove anything in the soundness case? So that's why we are sort of restricting our view first to the discrete case and trying to see, okay, can we answer things here? Can we understand something about the Steiner tree structure here?
What if something better is known or still this 1.39?
I think 1.39, as far as I know, is the best. There's no improvement on this. Okay, so this is done. But then there's, and this reduction again is from taking tight hardness result for 3-lin and then doing some very complex gadget reduction. I never believe that these will give you right answers. Like it will give you some answer, but never the right one. But then if you start from a very simple thing, like 3-set cover, you will get a very clean theorem saying if 3-set cover is hard to approximate to some factor, Steiner tree is hard to approximate to some factor, right? A very clean reduction. Like
by 3-set cover, you mean the size of each set is covered or the frequency?
the size of each set is at most 3. Let's say exactly 3. So if you take 3 set cover, and we know that it's 1 plus delta hard to approximate, then we can show, and I think I'll show this proof, that the Steiner tree problem on graphs is hard to approximate to 1 plus delta over 4. So proving the tight hardness result here will imply immediately here. And this doesn't need to be 3 set cover. You can take 4 set cover. You'll get a clean trade-off here. I think if you take B here, you'll get B plus 1 here. And then you can just try to get the best hardness approximation for set cover.
Other problems that will, like, let's say, vector with vacuum geometry, start with 3-dimensional matching, and it's hard to some factor, then some loss with 4 or 8.
Right. So I believe those are the right things to do, and you modularize your effort. So you can have people trying to just prove the right answer here, and then it immediately translates. I think this is the correct approach to do.
Probably delta set cover is, E set cover is the right problem, or you believe other problems may be better candidates for.
So we will see, depending on the geometry.
Okay.
So this is general metrics, right?
Yeah.
So Euclidean, you don't get anything from this. It's impossible. Like that's why it was open for even the discrete case. So for Euclidean 3 set cover, you get nothing. But if you take 3 set packing, then you get something. And it's very interesting to see for L1, for instance, set packing gives nothing. But for set cover, like the vertex cover version, gives you the right sort of possible bounds. So these sort of interplay happens with the geometry between packing and covering.
The shift, I think for LP norm, till some value of P.
Yeah, it's very fascinating. It's a ln 3, log 3 4/3, which is like 3.8. From there, a mixture of packing and covering gives the right thing. At infinity and 1, it's covering, and at 2, it's packing. So there's this very nice thing happening, and it's to do with the Steiner tree geometry. Okay, let me just quickly sketch the proof of this so that we're all on the same page. So you have an instance of 3 set cover. So you have sets, and so you can associate with this classic bipartite graph, which is the membership graph. These are the sets, and here you have the universe. So you have S here, and it's connected to an you put an edge between U and S if U belongs to S. So it's just a membership graph of any set system. And then the Steiner tree instance that we create is going to be the universe elements are going to be the terminals. So this is going to be the set P. Okay, and these will be the facilities. We'll do one small addition to make the proof clean. Is we will take a root and also include it in P and connect it to everyone here. So we take the bipartite graph coming from any set system and take an additional vertex, which is the root, and connect it to all the sets. So this is the instance of our Steiner tree where we are given this graph, and we have noted that this set here and the root are our set of terminals. In the S case, right, there is a set cover of size K such that if you look at any universe here, I'm able to pick, say, some bunch of people here such that they cover everyone. Right? And then all of these I just connect it to the root. So the cost is going to be the size of the universe plus the size of the set cover. In the soundness case, take any Steiner tree. For every universe, the only way to get connected is to connect to an edge, to take an edge to a set. So look at the collection of sets that we have here, which are in the Steiner tree. That should form a set cover. So if we had a gap, you'll get U plus K times 1 plus delta. And suppose K was a partition, let's say in the 3 set cover in the yes case. So K would be U over 3, right? So here you get 4/3 U, and here you will get the same thing, 4/3 U, 1 plus delta over 4. That's basically where the factor comes in. So let's assume that in the yes case, you have a partition. So your all sets are of size 3, and it's a partition, right? So you have K would be equal to U over 3. So the cost of the Steiner tree is going to be 4/3 U. And here, it's going to be 4/3 U times 1 plus delta over 4. Because if you just if you expand this, you'll get this expression.
It's a graphical metric that you are working on. I mean, the graph could be animated and the distance.
Yeah, I haven't seen like nice problems where the weights really help in hardness instances. They're a very big issue for algorithm people, but it usually is more of an issue algorithmically. Right, so this gives us a reduction. It's very clean, and the state of the art for 3 set cover is 7/6 approximation. So if we had 7/6, I'm not sure 6/5. 6/5, and this would imply that Steiner tree, if this was tight, then it would imply Steiner tree is hard up to 1.05. Okay, good. So that's already a start. So it gives motivation both from a hardness and approximation to study these bounded set systems. Try to get the right answer. So, but the topic of today is studying these in LP metrics. So, what do we know in LP metrics? So, the only result, yeah,
is approximation ratio.
right? It's the approximation ratio.
Hardness.
Hardness for 3 set cover would be again something like 1.01 by the same people. CC, like basically they have written like I don't know, like 5-10 papers where they take 3 lin and then just do gadget reductions to everything, and so you get 1.01 for more or less all the problems. So LP metrics, the only thing we knew was for L1 from Trevisan. And this, it's not written explicitly in this form, but what it says is that if you have 3 vertex cover and you have 1 plus delta hardness approximation for this, then you immediately get for Steiner tree in L1 1 plus delta over 4. Three or max degree 3.
In that case, going to 4 or 5 set cover is not beneficial.
It might be because the hardness gap might be higher. We don't know the interplay between these things. And this reduction is essentially the same as this. So let's rewrite vertex cover as a set system. You will have the edges. So vertex cover, you're given a graph and you want to find the smallest number of vertices such that every edge is being hit or being covered. So you just take the edges here. So this is your universe elements or terminals, and your vertices are here, which are your facilities. Then you just take your candidate root Now there's a natural, let's say the vertices, I associate n, the set 1 to n with them. Then you can just do an embedding in L1, which is in the most natural way, which is just E1, the standard basis vectors, up to En. Every terminal, which is an edge, is just two vertices. So you associate it with Ei plus Ej, if this was an edge between I and j vertices. Okay? And now notice that the same reduction will just go through. And the root would just be the all zeros vector. So everything here is at distance 1. And everything here, whenever they have an edge, is at distance 1. So the reduction just goes through. It's a very simple reduction. And then you can do some work to bring the dimension down. This n dimensions, you can bring it down to log n. And that's tight. You can't bring it below log n. Because the fixed dimensional PTAS will be sub-exponential time below log n dimensions. So if you assume ETH and things like that, you can't go below log n dimensions.
There are two things. One is approximation factor that you get. So as you go for k-set cover, it gets harder and harder. Hardness is also harder on log k or something.
Yeah, yeah, exactly. So the
other thing is fourth third U that you're getting. So if you have large k, then that value will go down.
Right.
So it's a balance. So
yeah, because set cover grows at log rate, and this going down at like linear rate, so that it's not beneficial. So, but these reductions, whatever you try to do in Euclidean, they'll just completely fail. And this is very counterintuitive because in clustering, just vertex cover gives you everything. And to some extent, even PSP, you can get almost everything you want from vertex cover. So this is very strange that somehow things are just failing here at Euclidean. And it's for a good reason. So you'll now see a reduction. So let me just take the main result and then show the proof for Euclidean case to as much detail as I can. So theorem for all LP metrics. There exists an epsilon greater than 0, which might depend on the P, such that Steiner tree is NP hard to approximate to 1 plus epsilon factor. So this is the main result of our work. So this itself is already good because now we say that there is no PTAS for all LP metrics. You can also get it for free for edit and Ulam because there are these isometric embeddings that do it.
So you said only for L1 this hardness was known. I mean, it takes, let's say, one perception.
Right. I mean, immediately because of these are general metrics and there's this thing called pressure embedding, you get it for L infinity as well. So L1 and L infinity was known. Now we know it for all LP. But the more interesting thing is the connection. So let me define what is called the epsilon delta set packing problem. So here you are given a set system where sets are of size. Yeah.
epsilon is different for each P or?
Yeah. We will see. I'll write a precise expression. It will be different for each. Like P will come in. That's what I'm trying to say.
How would it increases over P? Like what is the relation?
We will see. It's very weird. And we're not even trying to optimize it, right? Like we just wrote something and already is very weird.
Only deal with P being integral or?
No, it doesn't matter. Because the embeddings go through anyway. As long as it's greater than or equal to 1. Otherwise, it's not a metric. So epsilon delta set packing problem. You're given a set system. Each set is of size at most 3. That's why it's SP3. And in the completeness case, you have n over 3 disjoint subsets in the collection. So this forms a partition, and we're all good. In the soundness case, we want 2 things. One, that every set cover must be of size 1 plus delta times n over 3. And if you take any collection of pairwise disjoint sets, they span at most 1 minus epsilon times n of the universe. So every set cover is size at least this, and every collection of pairwise disjoint sets is of size at most 1 plus epsilon times n over 3. One minus epsilon. In the S case, you are able to get n over 3, many of them. Here you get 1 minus epsilon. So you get both of this. And now, assuming this is hard, which it is for some epsilon and delta, we can show a clean reduction to Steiner tree and LP metrics. Notice that delta is bounded. It's between epsilon over 2 and 2 epsilon. Why? Because if you are in the soundness case and you already have someone covering up to 1 minus epsilon times n over 3, you can either have the remaining being covered by sets of size 3 or sets of size 2, because 3 would have been disjoint, or singleton. So you get that delta is between epsilon over 2 and 2 epsilon. So now the main theorem. Assuming epsilon delta SP3 is NP hard, SP in LP metric is hard to approximate to this value. So when p equals to infinity, it's clean. We just saw this blue. So this when p is infinity. Okay. And then there's a weird expression which I'll write here. So I should copy it. And this is believed to be the right thing for reasons I've explained. So it's epsilon over 2 times 1 minus 1 over 3 to the 1 over p plus 2 delta. So you can see that whenever I use epsilon, I'm using the packing. How much is coming from the packing? Whenever I use a delta, I use how much is covering from the covering properties. So at infinity, the packing properties are useless. Only the covering helps. And between p infinity and 3.8, you need both. So this is when p is greater than 1 over log 3 of 4/3, which is roughly 3.8. So for every p greater than 3.8, you have this expression of trade-off between epsilon and deltas. And then at exactly p equals to 3.8, you don't need anything from the covering. So you get epsilon over 2, which is a clean expression. And from this point on, it's unclear if you need at all any covering. And in fact, for the Euclidean case, you get epsilon over 26, which the delta is not helping at all. So all you need is the packing properties of set cover. And at p equal to 1, packing doesn't help. So we don't know what's happening between 1 and 2. But at p equal to 2, only the packing is helping. And at p equal to 1, only the covering is helping. Okay. Good. So the general proof written in the paper is like quite. So we take any set system and say, look at this bipartite graph we have, and you can think of, okay, take any embedding into LP metric space as long as they satisfy some distance properties. Like say this some distance, we can embed such that these distances are realized. And if conditions 1, 2, 3, 4 hold, then you get hardness approximation to this factor in this metric space. So we have a generic theorem like that, but it's very convoluted and it's notation heavy. So I'm going to just show it for Euclidean by just assuming a specific embedding.
So the gaps are not known, I mean, between 2 and 3.8 or 8.
Oh, we didn't bother to. There is an expression which you can optimize. We just didn't bother to find the embeddings. You can just show it's greater than 0. That's easy to show.
Isn't the hardness really like this, or it's basically a bottleneck coming from the reduction or properties of sector? Or you really think problems are harder and then become easier in some way as speed grows?
Yeah, I mean, so this phenomena is common with clustering as well. My real belief is that we need even more structured instances. These are not along the wrong way, but the embeddings can be improved with even more structured instances. And I know how to do them for Euclidean in clustering. But then those become almost impossible to prove hardness results for, although we believe it. So I believe that's something like this. Like these can be improved, but then you need much deeper hard instances. Like just to give you an example, in clustering or whatever, if the host graph is a subgraph of the Boolean hypercube, like the hard instances we build implicitly can be written as a subgraph of the Boolean hypercube, then we can get better embeddings in Euclidean metric, which are still very natural, which would be take the midpoint. Once you embed it in the Boolean hypercube, take the midpoint of the edge. That will be an embedding of an edge. So very natural things. But then we have no idea how to prove hardness approximation for these vertex covers. Okay, so I'm going to just assume, let's say, set packing. I don't need anything else, right? Like, so I'm in what is called 3-dimensional matching. Like you can think of it however you want. So the embedding is as follows. So I will even think of it as disjoint triangles. Given a graph, in the yes case, you can partition the vertex set into n/3 disjoint triangles. And in the no case, you can partition it only, you can only cover 1 minus epsilon times n many vertices using disjoint triangles. The disjoint triangles problem. In the yes case, there are n/3 disjoint triangles. In the no case, there are at most 1 minus epsilon times n/3 disjoint triangles. And what is the embedding? So every vertex, I think of it as the point EI. So the ith vertex is just EI. And these are my terminals. Notice we are moving away from vertex cover. So vertices become terminals. And the Steiner points, which are the facilities, are the triangles. So if I take a triangle, let's say IJK is a triangle in the graph, then I associate it with it to the point EI plus EJ plus EK, the whole times 1 over 6. So there's a scaling that happens. And it's very important, this 1 over 6. So this constant here, 1 over 6 is like 0.18. It needs to be less than 0.31 for the reduction to work. So you can't put 1 over 4 or things like that. And you will see why it's needed, it will come out very naturally in terms of how the Steiner tree looks. And 1 over 6 is just optimizing certain inequalities. So, and then we have the dummy root, which is the all zeros vector. So let's look at how the Steiner tree looks like, the input graph. So here you have the E1 up to En, which are the terminals. And here you have the triangles, which are of norm. So here this is like EI plus EJ plus EK, the whole 1/6. And then you have this dummy terminal, which is also there, which is the zero vector. Just to make sure, look at this distance. This distance is significantly shorter than any distance here. And that's an important feature that we need. So this distance is, what is it? It's 3 over 36. And even if here I take the distance from EI to EI plus EJ plus EK, it's going to be much more than 3 over 36. Okay, so this is the thing. Good. So in the completeness case,
that's why you need 3.1 or some value. 1 by 6. Instead of that, you can take something like less than 1 by 3.1 or something.
I can take anything. This thing, I can replace 1 over 6 with anything less than 0.31.
Is it because of this property that you want to make sure the distance between?
No, it's not discrete. It's going to be needed because in the optimal Steiner tree, in the completeness case, it's going to look exactly like how we thought. These are the terminals. These are specifically the disjoint triangles, and you'll get a nice tree branching out. 3 here, 3 here, 3 here, 3 here. In the soundness case, I want to rule out edges which are of the form like this, between Steiner points, which don't exist in the completeness case. To rule these out, I need this thing. Because if these happen, I have no control over how things are happening. Okay, so let's prove some structural. In the completeness case, we are done, right? Like in the completeness case, the Steiner points I pick are exactly those disjoint triangles, which are n over 3 of them, and they're going to have distance, whatever the distance here is. I'm going to compute it, and then these things will be connected to the all zeros. So in the completeness case, we have n over 3 times square root 1 over 12, because that's the distance from a Steiner point to the all zeros, plus n times the distance from a triangle to a vertex that is in the triangle, which is going to be, what is it going to be? 1 minus 1 over 36. Can someone tell me what the answer is?
37.
Is it going to be greater than 1? Yeah. 37 by 36. No, I'm fine. 27 by 36. So that can be simplified to 3/4, right? So you'll get some expression like this. And you want to claim that in the soundness case, is going to be more than this.
Be 3 times, right? Because you're putting the distance from here.
Yeah, that's why it's n and here and over 3.
Oh, sure. Right.
Okay, in the soundness case, let's start looking at some structural properties of the Steiner tree. First, let's look at the terminals. I want to say that the terminals look like leaf nodes to start with. Like take any optimal Steiner tree, all the terminals except the zeros vector should be like leaves in the thing. And in order to say that, I need. So let me write down a bunch of claims and then prove each one by hand or not rigorously, but like I'll just show pictures to show the proof. The first one is that in any look at any optimal Steiner tree configuration, there will only be an edge from EI to a Steiner point if that Steiner point contains the vertex I. So EI, comma S is an edge in the Steiner tree if and only if I belongs to S. Okay. Why is this? It's because if I does not belong to S, then I can just remove this edge. Now I need to connect I. I'll just connect I. So when I remove this edge, either I or S is disconnected from the zero vector because it's a tree. Whichever it is, I will just add that edge to the zero vector. That is going to be a shorter edge. From I to 0, its cost is 1 because it's EI to 0. From S, it's even less than 1. But if I does not belong to S, then the cost is going to be somewhere you have 1, 6, 1, 6, 1, 6 on 3 coordinates, and then you have a 1 on a different coordinate. This cost is more than 1. So I'm removing an edge of cost more than 1 and replacing it with an edge of cost at most 1. So this cannot happen, right? So that's why we have that only has edges to the triangles that it's contained in. Okay, good. Then the next claim, which is also straightforward, is that there is no edge in the optimal Steiner tree between two terminals, because any two terminals are at distance square root 2. If such an edge exists, I will remove it. Then either this guy or this guy is going to be connected to 0 in the connected component of 0. Whoever is not connected, I just put an edge to 0, and that's going to be a cost 1 edge. So there is no terminal edge. Finally, I want to say that in the optimal Steiner tree, everyone here looks like a leaf. So if it doesn't look like a leaf, there are two possibilities. Either I have some EI here who is connected to two Steiner points, or I have an EI here, so let's say S and S prime, or I have an EI which is connected to the all zeros and some Steiner point. In either case, I can remove something. Like for instance, I can remove this edge, okay, or this edge, whichever is connected to all zeros. And then I can just introduce an edge to 0 here. This is a shorter edge. Remember that we said that the edges from the Steiner points, this is shorter. And the same with this. I can remove this and then just connect it to this. So the third claim is that all terminals appear as leaves in the Steiner tree. So these are the easy claims. Then the more difficult one, which is basically the heart of the proof, is to say that there is no edge between two Steiner points. So I want to say that there is no in the Steiner tree. And once I say this, I'm more or less done, because then I have like the structure which I wanted. All the edges look like this. And moreover, we'll have that if some guy here has just two neighbors, then I can just drop these two and then directly connect them here to one of the things, and I'll be done. So everyone will look like disjoint triangles. So the whole heart of the claim is to show that there is no Steiner edge. Okay, let me just sketch this proof. So we know that if there is such an edge, let's assume for the sake of contradiction, then the two Steiner points, which are basically two triangles, must overlap on an edge. So if S is some ijk and S prime is some ijk prime, then we are fine. We don't have any contradiction. But if it was just overlapping on one thing or none, then they're already too far away. Just when you make the computation. So I can remove that edge and put them to 0. So they overlap on exactly two elements. So let's look at some S and S prime which overlap on two elements. So let's say this is a S, this is an S prime, and they overlap on ij. Now there might be other S double prime which also overlaps on this, but I'm going to focus on a specific S. So for instance, if there's another S double prime which also overlaps on two elements I and j, then I'm going to fix S, remove this edge, and put this edge instead. And the Steiner tree cost remains the same. So I'm focused on a specific S which has one of each kind at most. Okay. So once I have this, then I want to claim that this S must be adjacent to one of the terminals. Why? First of all, notice that any Steiner point must be of degree 3. If it's of degree 2, then by triangle inequality, I can just remove it. So if it's of degree 3 and it does not contain any terminal, then there are two possibilities. Either it's connected to 3 guys, like this, in which case I can just remove this and I'm fine. Because these distances I can remove it and connect them to the 0 thing. One of them to the, two of them to the 0 thing. On the other hand, if I had something like S prime, and the 0 vector, then too I'm fine. I can remove this and connect it to this.
Generally, Euclidean metric can have weakly coded. It seems like.
Yeah, I mean, if you do the continuous case, you can formally prove any optimal Steiner tree will have 3 things because of the angles. So that's why we can assume that every the S here will be adjacent to some terminal. So now, but if it's adjacent to one terminal, then there are 2 cases, right? Like, so let's say it's adjacent to some terminal EI. And so this is S prime, S double prime. Either there are 2 such S prime and S double prime or just 1. But if there are 2 such S and S double prime, that means the union itself covers all the terminals that are there. So if this was some ijk, and I know this is some ijk prime, and I know these 2 overlap on 2 elements as well. So I can just use S prime and S double prime to cover all the terminals covered by S. So I can get rid of S. And the same will hold in the other case as well. So I can always just replace such a thing. So such an edge S prime cannot exist. I'm skipping a few details, but This is the whole point. Okay, so this gives basically the result as stated. So what we have shown is that in the optimal Steiner tree, it's good to pack as many triangles as possible, and the remaining terminals should just directly connect to all zeros. So pack as many as possible and then do a singleton connection. So the cost is going to be, in the sumless case, you have at most 1 minus epsilon times n over 3 triangles, and each of them are going to be paying that cost. Right, so it's 1 minus epsilon times whatever that cost is. Plus for the remaining, I just connect directly to the all ones vectors, right? So I have epsilon n paying 1 and the remaining paying that. So that gives the hardness approximation factor, which is epsilon over 26. 1 plus epsilon over 26.
The same kind of idea goes through with for different pieces. Right?
No. So there are many things that are simplified in the Euclidean metric. Like Steiner point, all these ideas we showed that the calculations work out, they don't work beyond p greater than 3.8.
Beyond 3.8.
So there we use the covering property. So that's when you say, okay, I can't say things will be like either covered by triangles or by singletons. So I will have people who are covered twice and overlapping and things like that. But I know the set cover size is large. So we use there the set cover properties.
For all P metric, like what is the worst case bound if you get to general metric in FP, improving the 1.01, 1 point, whatever the previous value was. Do you do something here?
Yeah. I mean, explicitly, these problems are not studied like 3 set cover, 3 set packing. We don't have good bounds. So we end up getting exactly their thing from the state of the art because those things are also given by them. I mean, they are using roughly this, but if you start believing, okay, so I have like some ongoing work where for 3 set packing, this recording, okay.
I can stop recording. We can stop recording. Okay, this topic is finished, right?
Yeah, topic is finished.
Then let's stop recording.
Okay, now